The Vital software architecture is designed to facilitate the tight coupling of a set of core simulation modules with a high-quality interactive 3D visualization. The architecture adopts a computational steering model in which the user guides the behavior of the simulation models through the user interface and receives feedback through the visualization. This approach enables users to explore the predicted geometric variation within, within the assigned tolerances and immediately assess the impact of the variation on the aesthetic quality of the model. This is the flow chart in which we would have the complete procedure in which the Vital works. Now let me start with interaction model. The interaction model provides the interactive user interface to the system and enables the user to steer the simulation with the environment. Now let's go for the environment model, which simulates a photorealistic environment in which the product resides and generates a realistic lighting model for the product. Then the tolerance model, which gathers and filters the results on an offline tolerance analysis to simulate the effects of different tolerances scenarios, such as most likely worst case and best case conditions, and enable what-if studies. The deformation model simulates the effect of component deformation as a result of different tolerance conditions by deforming the geometric representation of the components, and the assembly model, which you can see it here in the middle, represents and maintains assembly constraints between components and support the interactive assembly and disassembly of the product within the environment. Finally, the behavior model simulates the physical dynamic of the product within the environment, maintaining consistency against physical laws such as gravity, friction, contact, and contact dynamics. Here, after we completely did these Vital tools, we use some third-party tools like clear code rendering, PQP, collision detection, and math engine dynamics and OpenGL optimizers, which are third-party tools, which we are not really concerned about. And then we would have and then we would visualize the results, and we receive feedback of them. In this way, we would be able to see exactly what happens by the variation of different components. I mean that in this way, we see everything, and we can have control and access on everything that we are struggled with. So let's ask why we use Vital. Let me say that it is to determine how part and assembly tolerances affect the overall build and fit of a product. In other words, we need to answer so many questions like, will my current design work? Or if yes, how well? And where should I measure in production? Where will I have manufacturing problems specifically? How will tooling affect my product? Can I change the assembly process to reduce variation, or how to fix the variations? Okay, I'm not familiar with what you have said. What is GT power? No, no, we are not speaking about GT power. It's completely about the exterior of the vehicle. I mean that we are speaking about the new developments regarding this field. So let me continue. You see, we are speaking about design. In the procedure of Vital, first we would have the design and gap and flushness objectives and tooling design. Then we would simulate by using a Monte Carlo simulation method. Then we would validate by the concept of sensitivity analysis. After that, we would redesign, and we study the what-if scenarios, and finally, we would produce the vehicle. Okay, so let's speak about the leading software solution regarding this field. The most famous software regarding this field is the 3DCS, which is used by the leading manufacturing OEMs to reduce their cost of quality by controlling variation and optimizing designs to account for inherent process and part variation. Engineers reduce non-conformance, scrap, rework, and warranty costs. You see that this CAD and this software would be integrated by different CAD softwares like CATIA V5, CATIA 3D Experience, Siemens NX, and Pro. In using this software, it can show us what really happens. I mean that this software is an example of that vital structure that you didn't like it, which I was talking about it. This can show you what really happened during that definition of vital. Here, we determine design objectives with high-end visualization. We create a model to simulate a product and process variation. We run analysis to determine contributors and critical to quality features. Then we create reports and collaborate. And then we would make changes, and we can test our new design. You can see everything is controllable in that sensitivity analysis of the outputs of the software, which are these. Means that there are so many information after we receive, after we have uploaded our inputs, then we can see everything. Okay, take a look at these pictures, which you may like more. This shows the gap between the hood and fender. Here is the hood and here is the fender. And this is the gap between them. This is the normal size of the gap, which probably is considered by the stylist. Here, we see that the gap has increased, and this is the maximum gap during the design, which the software can show us that. And this is a really unpleasant gap style, which is named as AV gap. If this happens, we should absolutely change our procedure by changing anything like fixings or hinges of the hood or the fixings of the fender. But I want to say that this software shows everything like this, and this is the result or outcome of the software, which can help us during our design procedure. Now, let's talk about the leading hardwares. There is not any specific hardware for this gap and flushness definition because gap and flushness calculation and optimization is basically a pre-manufacturing operation. So there are not any tools and instruments but the mentioned analytical software or mathematical manipulations. However, there are some tools to measure the gap and flushness after production to check out whether their values are in the range. There are myriads of measuring tools basically working with optic, I mean the concept of optic, to measure the gap or flushness in the manufacturing line as a part of quality control procedure. So look at that. You see here the optic, which is now in this picture, is measuring the gap between the hood and headlamp. So the procedure working them could be divided into 3 different portions. First, they could be measured by some robots here with such shapes that are measuring here the gap between the fender and door, which are placed in the manufacturing line and called as automated inline. Then after the painting, we would have a painted car here, which again can measure the gap and flushness by these handy tools. And then after the complete production, we would have an upline gap evaluation with this tool, which again do the same thing. Here again, you can see a complete picture of measuring the gap and flashnesses, and data and results could be achieved and would be illustrated in this style. You can see here that the gap is measured here as 4.7 and the flushness is minus 0.1. And the orange ones are those which are near to the failure, and the red one is showing the failure. I mean that this is a contradiction with what we have defined or considered for the gap to be. But the blue or green ones shows that we are in the safe side. Now, let me tell you about the technical content in the course. You see, we need some prerequisites for learning how we should calculate the gap and flashnesses. You need to have an understanding of basic drafting techniques. You need to have an understanding of basic design techniques. I mean, that CAD design or such things. You should have the ability to create 3D models in a CAD software, preferably CATIA V5. And you should have ability to create 2D drafting in the same CAD software. But what really you are going to learn is first how to section in CATIA V5, which is so easy. Then I will teach you the GD&T symbols and datums, which are these things you can see here in the picture. Then I would teach you the general tolerances, geometric tolerances, which are all these symbols shown here and are not that much difficult to learn. Then I would speak about the most crucial thing that you will learn here, which is the stack-up analysis. And I would speak about this section very comprehensively. Then we would have the tolerance analysis, which is a review or combination of all things here. Then I would speak about the root sum square method, which is a calculation. I mean, the mathematical method, which helps to understand what would the gap and the final gap and flashes be like. Then we have Monte Carlo simulation, which I'm not going very deep because it is a advanced thing, same as high-low median analysis and G-factor analysis. These things are not being very discussed, but I just introduce them because they are mostly being used in the softwares that that is out of our syllabus. Now let's speak about the most important thing, which is the job roles which could be provided by learning this course. As you know, this gap and flushness, or this course basically is being applied in automotive industry, in aerospace industry, in rolling stock industry, in home appliance, electronics like mobile phones or other gadgets, and in medical machines or any other industries in which some products which are the result of some assemblies would be manufactured. As a junior position, for those solid mechanic, applied mechanic, manufacturing engineering graduates from universities, we would have some roles in junior level, which are mechanical engineer, CAD designer, R&D engineer, product engineer, and development engineer. In these roles, this course would be beneficial. In what way? I will tell you. Engineers are regularly responsible. I mean that after you enter a company as a fresh graduate person, you would be responsible on being able to interpret the tolerances and other variations which affect the final product upon flushness. I mean, if you go to a company and you are hired if you are going to work in a design department, you would absolutely need to be able to do these things to tolerance and to be able to do the tolerance analysis to learn how to do them. Then you would have the chance to participate in design teams and collaborate in the process of defining components tolerances by assisting the senior engineers. Here, you will learn the skills which the course provides them with, by learning the things that this course provides you with, you would be able to enhance your technical capabilities and to achieve job promotions as a result of working within expert teams. But in senior positions, which are those mechanical engineers by more than 5 years work experience, which would be lead engineers, lead design engineers in the companies, supervisor of design engineering teams, or tolerance engineers. Here, responsibilities are conceptualizing sophisticated designs and analyze or select materials and processes. You would be responsible for developing and designing high-quality, modifiable 2D and 3D CAD models, performing and reviewing tolerance calculations, performing component and machine cost analysis, and creating models and drawings in the appropriate software. By learning this field, you would be absolutely able to do all these tasks as a senior mechanical engineer. And in the top management positions, for those engineers who have more than 8 years of work experience, like project managers, mechanical design director, or managers, the persons who have the responsibilities like cooperating with a styling department, achieving the final design of the product. They recruit, retain, and develop a team of experts to design the product based on the design criteria. They will lead the team in defining principles for tolerance and stack-up analysis, and they will interpret the manufacturing criteria into design definitions and guide the team to make changes and do improvements. I mean, these persons, by knowing the aspects and foundation of stack-up analysis or gap and flushness, are able to do all the related things of design. Here, during the course, we would have a case study, which is a vehicle like this, and it's a real model of a car, which I bring the render of that here. And we would analyze the gap and flashnesses of these areas that you can see is related to the side panel of the vehicle, of the exterior body of the vehicle. And since all the values are real, this could be really beneficial for the students. And let me tell you how to get into this domain. First, you would need to have a basic math knowledge. Then you should be familiar with Microsoft Excel, which is obvious. Then you should be familiar with main components and assemblies of the vehicle, not GT power, just the common components. And then you should be able to create 2D drawings and dimensions. And you should have basic CAD skills, preferably CATIA V5, and then you could get into the course. So here are the references to complete this presentation. And